Today we have a last lecture on machine learning. Today we will talk about probabilistic learning, and maybe if we have some time we will discuss a little bit about computational learning theory. You have earlier learnt about uncertainty and probabilities. So, what we discuss now is how Bayesian learning can be used for the sort of concept learning tasks that we have been looking at in this class. So, you have already looked at some simple machine learning algorithms that are used for concept learning. For example, you have studied decision trees and looked at algorithms for top down training of decision trees. In the last two classes, we have also looked at neural networks. So, mainly multi-layer feed forward neural networks, and we have seen how to train the neural networks using algorithms like backpropagation, so that the neural network can recognize the concept. Today, we will see that the Bayesian learning framework also provides some ways of concept learning, and we will also discuss the applications of these things as well as their limitations. Now, first let us discuss why is Bayesian learning an important framework to study. So, firstly, Bayesian learning provides many practical learning algorithms. For example, today we will discuss a very simple learning algorithm called knife based learning, which is especially easy to learn and to train. And then we will also discuss that this surprisingly simple method works quite well for certain classification tasks, and it is widely used for applications such as text classification and other areas. Then if you want to have more sophisticated learning methods, you have already learned about Bayesian belief networks in this class. It is possible to learn also Bayesian belief network. However, in this class we will not go into the details of the belief network learning. However, we will discuss that in the Bayesian learning framework, it is possible to easily combine prior knowledge. So, if for example, in the concept learning problem, what you are trying to do is try to find that hypothesis which is most likely to, you are trying to find out you are trying to learn a concept, you are trying to represent a concept, and you are trying to find out an hypothesis which is a good representation of the concept. Now, if you have some prior knowledge on which hypotheses are more likely, for example, so we will see that the Bayesian framework allows you to integrate this prior knowledge into your learning method, so that the hypothesis that you output, the posterior hypothesis that you output depends on your prior probabilities or prior knowledge about the hypothesis. Also, Bayesian learning provide foundations, many foundations for machine learning, and the Bayesian description, the Bayesian approach can be used to evaluate learning algorithms, including other learning algorithms, and it can be used to guide the design of new algorithms, and it allows us to learn from models or meta learning. So, Bayesian learning is a very important concept. However, in this class we will not discuss a great deal of details about the various statistical learning frameworks, but we will look at some simple methods, so that it sets your way to learn about these things further. Now, let us now see specifically how is Bayesian classification useful. In Bayesian classification is useful for probabilistic learning. In probabilistic learning, we calculate the explicit probabilities for hypothesis. For example, if you are given some training examples, you can output more than one hypothesis, and you can attach probabilities with the different hypotheses. For example, let us say you have a decision tree and you have one or you give, so in neural network or decision tree you give only one hypothesis. When you are given your training examples, you come up with one hypothesis. But in probabilistic learning framework, it is possible for you to come up with multiple hypotheses and also associate the confidence or probability that you have in each of these hypotheses. The second property of Bayesian classification is that it can be used in an incremental fashion. Each example can incrementally increase or decrease the probability of a hypothesis. I just mentioned that you can find out the posterior probability of the hypothesis. And when you have processed a number of examples, you have a certain you attach certain posterior probabilities with the different hypotheses. As you see new examples, your probabilities can get updated incrementally. So, this is one advantage of Bayesian classification techniques that we will study today. Thirdly, it allows you to make probabilistic prediction. That is, as I just mentioned, you can predict multiple hypotheses and you can associate with each of them their probabilities. Also, the Bayesian framework provides a standard for optimal decision making. Even when you are not using this technique, but using some other technique, you can try to evaluate how well that technique corresponds to this model. So, we can try to evaluate the type of the hypothesis that a learning algorithm outputs, whether it satisfies the different criteria that we will study. Now, before we go into the details of some learning algorithms, I would like you to just refresh your memory about certain basic formulas for probabilities, which you must have looked at earlier. For example, the product rule is used to find out the product of the probabilities of A and B. Now, probability of A and B can be written as the product of conditional probability of A given B times the probability of B. It can also be, because this is commutative, so probability of A and B is the same as the probability of B and A, and therefore, it can also be written as probability of B given A times the probability of A. Now, as we will see that we can combine this expression, probability of A given B times probability of B equal to probability of B given A times probability of A, to derive a very important learning hypothesis called the Bayesian hypothesis, which we will see presently. But before that, let us look at some other rules of combining probabilities. The sum rule allows you to find out the probability of the sum of two random variables. Probability of A plus B equal to probability of A plus probability of B minus probability of A and B, or A intersection B. So, this is called the sum rule. And then we have the theorem of total probability. If we have events A1, A2, An, and these events are mutually exclusive, then we can say that probability of B equal to sum over all i's probability of B given Ai times probability of Ai. So, we can condition on the different Ai's and we can combine these, the weighted sum, to get the probability of B. These three formulas are often used in different manipulations of probabilities. Now, we come to a very important rule called the Bayes rule. As I told you earlier that this expression can be used to derive Bayes rule. So, from this expression we can write that probability of A given B equal to probability of B given A times probability of A divided by probability of B. Okay. And this we can rewrite in the form of this we can rewrite in the form of probability of H given D equal to probability of D given H times probability of H divided by probability of D. This follows from the previous expression that we saw. Now, let us see how we can interpret this. If you take that H represents the hypothesis and D represents the data or the evidence. So, in the concept learning problem, you are given some training examples or the evidence, and you have to find out a hypothesis which describes the concept. So, this can be represented probabilistically as finding out for different hypotheses. So, you can consider different hypotheses, you find out the probability of that hypothesis given the data, and you can evaluate this probability for all the possible hypotheses and output that hypothesis which is most likely. So, what we are trying to do is evaluate the probability of a given hypothesis given the data or the evidence that we have. Now, we can rewrite probability of H given D in terms of probability of D given H. Why do we do this rewriting? Because it is often easier to evaluate probability of D given H. So, if we can evaluate probability D given H, from that we can find probability of H given D, but we need some other factors. For example, we need probability of H and probability of D. Let us see what these mean. So, probability of H can be interpreted as the prior probability of the hypothesis H. So, before you have got any evidence, you have a set of possible hypotheses that you are considering, and you have your initial belief about the probabilities of each of these hypotheses. To you, each of these hypotheses may be equally likely, or maybe that you consider that some of these hypotheses are more likely than the others. So, PH denotes your belief about the prior probability of the hypothesis H. We can refer to this as the prior. Now, what does probability of D stand for? It is the prior probability of the data D or the evidence, which is not really very intuitively clear what it means. So, probability of D is the prior probability of the data. Then what does probability of H given D signify? It is the probability of the hypothesis given the data. So, after you have seen the evidence, what is your posterior probability, what is your current belief, posterior belief after seeing the data about the hypothesis. This is called probability of H given D. After you have seen some training examples D, you want to find out based on this training example what is the probability of each of the hypotheses. As you increase your training examples, this can become updated. Then what does probability of D given H signify? It means the likelihood of D given H. So, you are given some hypothesis H. What is the likelihood that the hypothesis could have given rise to the data? We will look at some examples so that this is more clear to you. So, once you have written these like this, so we can say that posterior probability. So, probability H given D is the posterior probability equal to PH is the prior probability. This is the prior probability, this is the posterior probability. And what is probability of D given H? It is the likelihood of the data given the hypothesis, and this is the PD is the evidence that you have. This is evidence and this is likelihood. So, you can loosely write it like this: posterior equal to likelihood into prior divided by evidence. Now, so this is the base rule that we have, probability of H given D equal to probability of D given H into probability of H divided by probability of D. Generally, we want the most probable hypothesis given the training data, that the hypothesis which has the maximum a posterior probability. We refer to it as H map. H map is the called the map hypothesis. The map hypothesis is that hypothesis for which probability of H given D is maximum among all the hypotheses that you are considering. So, remember in the first class on learning, we talked about the hypothesis space. It is the set of hypotheses which you are considering. Now, you want to find out, suppose your hypothesis space can be finite or infinite, but suppose your hypothesis space is finite. So, suppose there are 100 hypotheses in the hypothesis space. You want to find out the probabilities, the posterior probabilities for each of the hypotheses, so that you can find out that hypothesis for which the posterior probability is the highest. So, H map is that value of H for which probability of H given D is maximized. This can be written as argmax H given H included in H included in the hypothesis space capital H, probability of H given D. Now, if we apply Bayes rule to this expression, we can substitute it by the right hand side of this equation. So, we can say that H map is that hypothesis for which probability of D given H times probability of H time divided by PD is maximized. Now, you see, when you inspect this expression, you are trying to find out that value of H for which the combination of these three terms is maximum, out of which the particular hypothesis that you are considering affects these two terms, but not this term. So, that hypothesis for which this entire thing is maximized is the same hypothesis for which only the numerator is maximized. So, a map hypothesis is the hypothesis for which probability of D given H times probability of H is maximized. Now, so suppose you are given a learning problem and you are able to find out these different probabilities. You would like to choose the maximum a posteriori hypothesis or H map, and H map is given by argmax H is included in the hypothesis space, probability of D given H times probability of H. Now, as we discussed, PH denotes the prior probability of the different hypothesis. Suppose that initially you consider all hypotheses to be equally likely, then you can say that PH is the same for all H included in the hypothesis space. In that case, the H map would be that hypothesis for which probability D given H is maximized, if you consider PH is the same. So, this hypothesis, such a hypothesis for which only PD given H is maximized is called the maximum likelihood hypothesis, and this is called the maximum a posteriori hypothesis. Now, MAP and ML hypothesis give you the same hypothesis if the prior probability of all the hypotheses are equal, otherwise they might give you different values. Now, before we proceed further, let us just illustrate what we mean by prior, posterior, and how they affect the decision making by looking at a simple standard problem. Now, in this problem, your objective is to find out whether a patient has malignant tumor or not, and you are given the following. A patient takes a lab test and the result comes back positive. The test returns a correct positive result in only 98% of the cases in which a malignant tumor is actually present, and the correct negative result in only 97% of the cases in which it is not present. Furthermore, it is known that only 0.008 of the entire population have this particular tumor. So this is the data that you are given. What you have to find out? Whether the patient is likely to have malignant tumor. So let us say the data is the two possible hypotheses are the patient has malignant tumor and the patient does not have malignant tumor. You have to find out whether the probability of the patient having malignant tumor given your evidence is higher or probability of not having malignant tumor given the evidence is higher. Now, what is the evidence? The evidence is that the patient takes a lab test for which the result is positive. So, result of the lab test is positive and the lab test is taken to identify whether the patient has tumor or not. However, the lab test is not 100% accurate. Now, you are told that if the patient does have malignant tumor, the lab test returns yes only in 98% of the cases. In 2% of the cases, the lab test returns wrong result. It tells you don't have tumor when you actually have tumor. Also, it tells us that if the malignant tumor is not present, then in 97% of the cases, the lab test returns negative, and 3% of the cases, the lab test returns positive. Okay. So, based on this, you have to find out if the result is positive, how likely the patient is to have malignant tumor. In addition to this, you are given some other data that your prior probability on malignant tumor or not malignant tumor are not equal. So, only 0.008 of the population have this tumor, that is 0.992 of the population does not have the tumor. So, the prior probability of tumor is only 0.008 and prior probability of no tumor is 0.992. Now, so let us try to show you how to proceed in this problem. So, from the description given in the previous slide, we can write that probability of tumor is 0.008. So, we can write that probability of tumor equal to 0.008 and probability of not tumor equal to 0.992. These are your prior probabilities. Now, you are also given that if there is tumor, then probability of lab test being plus is 0.98, and if there is tumor, probability of the negative result in the lab test is 0.02. You are further given that if there is no tumor, then probability of plus in lab test is 0.03 and probability of negative in lab test is 0.97. Now, your evidence that you are given is that the lab test returns positive, and you have to find out the posterior probability of the two possible hypotheses, probability of tumor given plus and probability of no tumor given plus. So, probability of tumor given plus can be written by using Bayes rule as probability of plus given tumor into probability of tumor divided by probability of plus, and probability of not tumor given plus is probability of plus given not tumor times probability of not tumor divided by probability of plus. Now, you can evaluate each of these values from the data that you are given. What is probability of plus given tumor? Probability of plus given tumor is 0.98 and probability of tumor is 0.008. What is probability of plus given not tumor? Probability of plus given not tumor is 0.03 and probability minus probability of not tumor is 0.992. Okay. And what is probability of plus? It is not known to us, but it does not matter. When you have probability of tumor given plus and probability of not tumor given plus, you want to find out which one of them is higher. You can find out which one of them is higher by only evaluating the numerator. Also, you know that probability these two sum to 1. You know that for any random variable, probability of A plus probability of not A equal to 1. So, you can take this 1 by probability of plus as some constant alpha, and you can say alpha times 0.98 into 0.008 plus alpha times 0.03 into 0.992 equal to 1. You can find out alpha and you can find the exact values of each of these probabilities. So, you need not know the probability of plus. So, I did not do the problem, but if you work this problem out, you will see that probability of not tumor given plus is much higher. And the reason why this is the case is because the prior probability of not tumor is much higher. Prior probability of not tumor is 0.992 and probability of tumor is only 0.008. If these two prior probabilities were equal, then probability of plus given tumor is 0.98 and probability of plus given not tumor is 0.03. So, definitely this would have been more likely. So, the maximum likelihood hypothesis is that the patient has tumor, but if we combine it with the prior probabilities on the hypothesis whether a patient has tumor or not tumor, we see that it is more likely that the patient does not have tumor. So, this example illustrates to you the role that prior probability plays in finding out the posterior probability. So, how does a map learner work? For each hypothesis H in the hypothesis space, so you have the hypothesis space capital H, and you are trying to find out for each hypothesis H in the hypothesis space, you compute the posterior probability, probability of H given the evidence, and you compute it using Bayes' rule, and then you output that hypothesis for which this is highest. So, the posterior probability H map is maximum, that hypothesis for which probability of H given D is maximum. This is called a map learner, maximum a posterior probability learner. So, you see that this is the Bayesian framework provides us a way of evaluating the probability of a hypothesis. In practice, the Bayesian method is not always, it is not always possible to apply the Bayesian method. Can you think why? The main reason is that the particular case that we considered, we had only two possible hypotheses in the hypothesis space. The patient has tumor or the patient does not have tumor. Consider a case where the number of possible hypotheses is very large. So, if you follow this procedure, for each hypothesis you have to find out the maximum a posterior probability, the posterior probability for each of the hypotheses, and you have to do it for each of the hypotheses. If the number of hypotheses is very large, it is not practical to enumerate each of the probabilities. So, therefore, this sort of rule is not applicable, but this nevertheless gives you a very good framework to show what is happening here. And if you study further into machine learning, you will see that many of the learning algorithms are evaluated based on whether the hypothesis that they output is a maximum a posterior hypothesis, is a map hypothesis or ML hypothesis or whatever criteria that satisfies. So, this gives a standard for judging the efficacy of different learning algorithms, and it can be applied when your hypothesis space is not very large. So, the map learner is computationally intensive because you have got to find out the posterior probability for each of the hypotheses. However, as I mentioned, it provides a standard for judging the performance of learning algorithm. You can analytically find out whether a hypothesis, whether a particular learning algorithm gives the map hypothesis or not. And by choosing PH the prior, it reflects a prior knowledge about the learning task. And probability of D given H also can be computed in many cases depending on our knowledge about how the hypothesis affects the data. Now, so far we have looked at map hypothesis. Now, let us look. So, map hypothesis gives you the hypothesis which is most likely. In some cases, the hypothesis, so it is not the hypothesis that you really care about, but you want to really find out the class. So, you have a concept learning problem, you are given some data, you are given a new example, and you want to find out the class of that data. If a hypothesis corresponds to a class, then a map hypothesis is what you are looking for. However, consider these cases that so is the hypothesis that is returned by the map learner, if that is applied on the instance X, does it give you the most likely classification of the instance X? It may not be the case. It depends on what form the hypothesis is in. For example, let us take a simple example. Suppose you have some evidence, D is your evidence, and you have 3 competing hypotheses. So, your hypothesis space consists of 3 hypotheses H1, H2 and H3, and suppose you compute the posterior probability of H1 to be 0.4, that of H2 to be 0.3 and that of H3 to be 0.3. Now, which is the maximum posterior, which is the hypothesis with the highest posterior probability? Definitely it is H1, because probability of H1 given D is 0.4, which is more than probability of H2 given D or probability of H3 given D. Now, suppose we pick now H1 and we apply H1 to X. Suppose we find out that when we apply H1 to X, H1 applied to X is plus, whereas H2X is minus and H3X is also minus. Now, what is the most likely classification of X? Okay. So, you can just look at these examples and see that the combined probability of H2 and H3 is 0.6 and they predict that X is minus, whereas H1, which has the single highest probability, it predicts that X is plus, but this probability is only 0.4. So, in this example, X is most likely is best classified as minus. Okay. Therefore, the map hypothesis applied to the instance does not necessarily give you the most probable classification of X. In such cases, what we really want is to find out a Bayes optimal classifier. Now, let us see what a Bayes optimal classifier is. So, suppose you have the different classes V. So, capital V is the set of possible classes. In your classification problem, capital V is the set of possible classes. The possible classes could be positive or negative in the case of the tumor example. Suppose you are trying to classify some news article as sports, politics, health, entertainment. So, your possible classes are sports, politics, health, entertainment. These are your 4 possible classes. So, what you are trying to find out is the class. So, the class Vj, which is an element of capital V. Capital V is the set of all classes, and you want to find out that class in capital V for which this quantity, for which this is the highest. So, you have different hypotheses H1, H2 etc., and all these hypotheses belong to the hypothesis space capital H. So, for each Vj you find out for each hypothesis Hi in the hypothesis space, you find out the probability that the probability of a particular value of Vj is sigma over all hypothesis probability of Vj given Hi into probability of Hi given D. So, this is the posterior probability of the hypothesis Hi, and this is the probability that the classification is Vj given the hypothesis I. So, suppose you have three hypotheses H1, H2, H3. The posterior probability of H1 is 0.4, H2 is 0.3, H3 is 0.3. Then what is the probability that your class is positive? It is probability of plus given H1 into 0.4 plus probability of plus given H2 into 0.3 plus probability of plus given H3 into 0.3. Okay. So, this is the probability of plus. What is the probability of minus? Similarly, it is probability of minus given H1 into posterior probability of H1 plus probability of minus given H2 into posterior of H2 plus minus given H3 into posterior of H3. So, let us try to apply this to the particular problem that we saw in the previous slide. So, we already seen that probability of H1 given D is 0.4, probability of H2 given D is 0.3 and probability H3 given D is 0.3, and H1x is positive. That means probability of plus given H1 is 1, probability of minus given H1 is 0. Okay. So, this is given to us, and we can therefore write as probability of H2 given D is 0.3, probability of minus given H2 is 1, probability plus given H2 is 0, probability minus given H1 is 0, probability of plus given H1 is 1. H3 classifies the instance as negative, therefore, probability of minus given H3 is 1 and probability of plus given H3 is 0. So, we can find out that probability of plus given Hi into probability of Hi given D over all Hi's gives us 0.4. You see, because there are three hypotheses H1, H2, H3, only H1 classifies this as positive, and so this expression is probability of plus given H1 into probability of H1 given D. Plus given H1 is 1 and probability H1 given D is 0.4. The rest of the things are 0. So, probability of the plus is finally 0.4, whereas probability of minus equal to 0.6. So, this is the most likely classification. Therefore, the most likely classification of the instance is negative. So, the Bayes optimal classifier allows you to find out, once you have found out the posterior probability of the hypothesis, you can apply the Bayes optimal classifier to find out the most likely classification of the examples. Next, what we will study is a classification algorithm which is called the naive Bayes classifier. It is a very simple classification algorithm, but quite effective in especially problems where the number of attributes is very large. So, the naive Bayes classifier is a popular simple learning algorithm. It works well when a moderate or large training set is available. To explain the naive Bayes classifier, we make a very restricting assumption, and the assumption is that the attributes that describe instances are conditionally independent given classification. So, what we are trying to say is, suppose we have some attributes A1, A2, An for a classification problem. we say that probability of A1 given C is independent of A2 or of the other attributes. So, the attributes are independent given the class. So, this is an assumption that we make. Now, this is a very restricting assumption. You are trying to say that these features are completely independent features, they do not interact. You see, in practice, in realistic learning problems, it is very difficult to find examples of attributes where all these attributes are independent, right. However, even with this wrong assumption, which does not hold for certain realistic problems, the output of the naive Bayes algorithm in practical problems sometimes is surprisingly good. And there are some applications on which naive Bayes have been applied and give quite good results, for example, in certain diagnosis problems. And as I mentioned at the beginning, in text classification, in many text classification, your objective is you are given some text document and you have some classes. For, as I said, it could be politics, sports, health, entertainment, etc. You want to find out which class this article belongs to. And for this classification task, naive Bayes algorithm has been quite successful in many such classification tasks. For example, there is a particular experiment that people have performed on the 20,000 news groups data set, where you have 20 news groups and you have 1000 documents per news group. And on this, naive Bayes was applied and it gave a classification accuracy of 89%, which is quite good. Now, let us look at what the naive Bayes classifier does. So, we assume that we have a discrete target function which takes you from the attribute space X to the class C. And suppose each instance X, small x, is described by the attributes A1, A2, An. So, there are n attributes A sub 1, A sub 2, A sub n, and you have a classification problem where C is the set of classes and X is the input instance. Now, what is the most probable value of Fx? It is given by the C map. C map is the class which has the highest probability. The class C with the maximum a posterior probability is that class Cj for which the following expression is maximized. Probability of Cj given the attributes. So, you want to find out C map is that value of Cj such that Cj is included in C, capital C, for which probability of Cj given A1, A2, An is maximized. We can rewrite this as we can rewrite probability of Cj given A1, A2, An as probability of A1, A2, An given Cj into probability of Cj divided by probability of A1, A2, An by applying Bayes rule. So, probability of Cj given A1, A2, An is probability of A1, A2, An given Cj times probability of Cj divided by probability of A1, A2, An. And since probability of A1, A2, An does not depend on Cj, we can say that C map is that class for which probability of A1, A2, An given Cj times probability of Cj is maximum. So, C map is that class Cj for which probability of A1, A2, An given Cj times probability of Cj is maximum. Now, you see probability of Cj we can estimate from either we can have some prior belief or we can estimate from the data that we have given. If you are given some training examples, and in the training examples we find out the proportion of examples belonging to the different classes, we can estimate probability of Cj. Now, the difficulty is to find out the value of this expression, probability of A1, A2, An given Cj. This is a joint probability of n attributes. Now, if we want to estimate the joint probability from the training data, we will require a very large number of training data. Why? Because we have n attributes. Even in the simplest case, when each attribute is Boolean, that is, each attribute can take two different values, the number of combinations of A1, A2, An is 2 to the power n. So, the number of such joints is very large. All combinations, if we look at all combinations of the attribute values, the number of such combinations is very large. Now, in order to estimate for each of them the probability, you require a very large corpus, and you also require a large number of values that you have to store. And this is clearly not doable when n is large. So, in the naive Bayes assumption, we make a very simplifying assumption. We assume that probability of A1, A2, An given Cj is product of probability Ai given Cj. We assume that A1, A2, An are conditionally independent given Cj. So, this can be written as probability of A1 given Cj times probability of A2 given Cj times probability of An times probability of An given Cj. So, we can write probability of A1, A2, An given Cj as product of probability of Ai given Cj over all i's. And therefore, C naive Bayes is that class for which this times probability of Cj is maximized. So, CNB is the class Cj which is a member of capital C, so that product over I, probability of Ai given Cj into probability of Cj is maximum. So, this is the naive Bayes classifier. It works under the assumption that the attributes are conditionally independent of each other given that you know the class. Now, so let us just recap a little bit. In Bayesian classification, the classification problem may be formalized using a posterior probabilities. We want to find out probability of C given A, probability that the sample tuple is of class C. You are given an instance x and you want to find out the probability that that instance belongs to class C. For example, suppose you want to know given the attributes of a particular day, whether it is a good day for playing. So, suppose you are given that outlook of the day is sunny, the day is windy and so on. I want to know whether it is a good day to play or bad day to play. So, two classes, yes and no. So, idea is you want to assign to the sample x the class label C such that probability of C given x is maximum. So, this is the problem that we are trying to solve, and naive Bayes classifier is one way of getting the solution, provided that the independence assumptions hold, provided that these attributes are independent given the class. So, outlook and windy does not depend on each other. So, whether it is sunny or cloudy does not affect whether it is wind or not, which may not be true. And then we have seen how to estimate a posterior probabilities by using Bayes theorem. Bayes theorem is stated as probability of C given x equal to probability of x given C times probability of C given divided by probability of x. Px is constant for all classes, and therefore, we want to find out that class for which probability of x given C into probability of C is maximum. But we cannot compute probability of x given C because x is an instance which depends on potentially a large number of attributes, and if you want to estimate each of these possibility, the number of such possibilities will be very large. So, in naive Bayes classification, we have made a very restrictive assumption, a naive assumption, which is that attributes are independent. That is, probability of x1, x2, xk given C is product of probability x1 given C, x2 given C, xk given C. Now, if the attribute ith attribute, suppose xi is a categorical attribute, then how do I estimate probability xi given C? So, what we can do is we can look at the training examples and find out for a given class how many times xi has a particular value. So, probability of xi given C can be estimated from the training corpus as the relative frequency of those training examples that have value xi as the ith attribute in class C. But if your attribute is continuous, suppose you have an attribute like temperature which takes continuous values, then Pxi given C is often estimated by assuming a probability distribution for these attributes. For example, often we assume a Gaussian density function from which probability of xi given C can be estimated. However, we will not go into those examples in this class. We will restrict ourselves to categorical attributes which are easier to handle. So, to recap, the naive Bayes algorithm works like this. In naive Bayes learn, you are given some examples. For each target value Vj, you estimate probability of Vj. Suppose you have this news group classification or news classification, you have 4 classes, sports, politics, health and entertainment. Now, for each of these classes, you estimate PVJ by looking at the corpus and finding out how many news you have from sports, how many from politics, how many from health, how many from entertainment. So, from this you can estimate PVJ. Now, for each attribute value, you can estimate probability of AI given Vj. So, if Vj is sports, you find out how many times this attribute A1 is true or A1 has a particular value. Just to give you a preview, in document classification, we often use the words that occur in the document as features. So, we look at the set of words that occur in the document. So, we want to know how many times the word referee is in a document given that it belongs to a sports domain, or how many times the word referee is in the document which belongs to the entertainment domain or health domain. So, we can find out for each attribute or each word that we are considering how many times that attribute takes a particular value for those documents that belong to that class. From this we can estimate probability of AI given Vj. Now, once we have estimated for all j probability of Vj, that is for all class the probabilities and all conditional probabilities AI given Vj, we can use those values to classify a new instance. So, the most likely classification of the new instance given by V is that value of Vj for which Pvj into product of Pai given Vj for all Ai is maximum. This is the naive Bayes formula for classifying a new instance. So, how do I compute probability of Ai given Vj? Probability of Ai given Vj is, suppose n denotes the number of examples in your training set for which the class is Vj, and nc denotes the number of examples in your training set for which the class is Vj and for which Ai has this particular value. Ai is that attribute has the value of Ai. So, probability of Ai given Vj can be estimated by nc divided by n. However, this sort of estimation has a problem that we will see is that You see, it could be that because you do not have sufficient number of examples, in your corpus, in your training data, there is no example with class equal to Vj and attribute equal to Ai, in which case this probability will be 0. And because you are taking the product of different probabilities, so if one of the probabilities is 0, the entire value would be 0. Therefore, in order to avoid this problem, we do some form of smoothing. So, we add in to ensure that the numerator is not 0, we add p, which is a prior estimate for probability of Ai given Vj. So, we ensure that the prior estimate is greater than 0, and if m is the weight given to the prior estimate, then we add mp to the numerator and m to the denominator. So, this is the smoothed value of probability Ai given Vj to ensure that this never goes to 0. In practice, we take p to be a very small value and m is the number of your examples. So, let us just illustrate it with an example. Suppose we are given the following data. So, we have some training set. In the training set, we have data corresponding to we have the different attributes of a particular day. For example, what is the outlook of the day? Is it sunny or overcast or raining? Is the temperature hot, mild or cool? Is the humidity high or normal? Is it windy or not? And we want to know whether it is a good day for sport or a bad day for sport. And from the data, we find out probability of Ai given Vj. If it is sunny, then this probability is of good day is 2 by 9, bad day is 3 by 5, and so on. So, we get this data of probability of Ai given Vj, and when we are given a new instance is described by the values of the attributes. In this particular instance, outlook is sunny, temperature is cool, humidity is high, wind is strong, and we want to find out whether it is a good day for playing tennis or a bad day. And we know that I have 14 examples in my training set, and 9 of them are good days, 5 are bad days. So, probability of yes is 9 by 14, probability of no is 5 by 14, and then we use the values in the previous table to find out the naive Bayes probability. So, we do not have time, so I will not go into this I compute this, but you can easily find out these values, and it comes out these are the values that come. So, just to recapitulate, the independence hypothesis that we make in naive Bayes makes computation simple, but is seldom satisfied in practice. And if we realistically want to model the problem, we have to use joint probabilities, which are not feasible, but the way out is to use Bayesian networks. You have studied Bayesian networks earlier in this course, and you can have algorithms for learning Bayesian networks, but we will not go into the details of this. With this, we end today's lecture. Thank you.